Video 3 of our current chapter, we're going to be exploring kind of a new idea here with the concept of probability with our geometry problems. Ooh, interesting, fun. So first we need to talk about some basics of probability. And so anytime mathematically that you would write the probability of an event, we use a capital P for probability, and then in parentheses you would put really what that event is that you're wanting to find the probability of. And I've got down here the event can really take on various geometrical ideas, especially this chapter, such as perimeter or area or surface area or volume of a particular region. Now, in general, probability is used in statistics, and so we might say that the event is a particular thing that happens instead of something geometrical. But we're going to stick with the idea of geometric probability. So down here we've got the probability of E of an event. I'm just shortening down event into a single letter now. That it's really equal to the ratio or the fraction of really all your favorable things that you want to happen for that event. And we want to divide it by all the parts that really could happen in that scenario. And for right now, you might be like, but what does favorable mean? What does all mean? We'll look at some examples, and you'll see specifically what I mean. The favorable part is like the event actually happening, divided by all parts could be like, not only will that event happen, but what is also the event not going to happen as well. That we have to consider as our denominator. Now, I've got probability set up here. I've got two n's that all probabilities, any event, is going to be between 0 and 100%. And so we're not going to go over 100%. We're not going to go less than 0%. But our answers will all be percentages, preferably. They could be decimals that could be represented as percentages between 0 and 100%. So here's a basic probability question. This has nothing to do with geometry, but just to give you a rough idea about what I mean, how are we going to set up that favorable part over the all part. So the first example, in a classroom, it contains 4 freshmen, 6 sophomores, 2 juniors, and 5 seniors. Then what is the probability of randomly selecting a sophomore from this class? So if I wanted to know the probability, and I'll just abbreviate sophomore, S-O-P-H, then I would need to consider, well, how many sophomores could I potentially choose in this class? And that is my favorable region. And so I have 6 sophomores that I could pick from. And then I would divide that by all the possibilities of people that I could pick. Well, I could pick freshmen, sophomores, juniors, or seniors in this entire class. Well, how many people are there in the entire class? Well, let's see. 4 freshmen plus 6 sophomores makes 10, plus 2 juniors makes 12, plus 5 juniors or seniors makes 17 total that's in the class. This represents that kind of all factor. That's our denominator. So essentially we have a 6 in 17 chance, and I could express this probability as a fraction. It doesn't have to be a decimal or a percent. But if I brought up my calculator, where are you at, calculator? There you are. And if I just typed in my calculator 6 divided by 17, and then multiply this by 100, not 1,000, to convert it to a percentage, this is roughly about 35 point, let's say 3%. So this is approximately, I have a 35.3% chance of just randomly picking one of these 6 sophomores from a class of 17 students altogether. So that's basic probability. Okay? Now we'll get into specific geometric probability questions. So now here's the first real geometric probability question. It says, what is the probability that a dart would land in the circle? And then we're going to have a follow-up question as what is the probability of landing inside the square but outside the circle? Now, some assumptions that we will unfortunately have to make here, but they are required, is that when we throw this dart, we're going to throw it randomly. We're not going to try to hit a particular area. And the other assumption is that the dart is going to land somewhere on this board, on the square board altogether. So there's no way that a dart could land out here. Because otherwise, then the probability, the denominator would be like infinity. If you could just spin around and throw a dart and it not hit the board, well, geez, you'd have infinitely many places that you could throw it. So we're going to say that the dart has to land somewhere within the square. Okay, the big shape in this problem, the square. Now, if I first started with that it would land in the circle, so we would say the probability that it lands in the circle is equal to, well, how could I measure something about this circle that it could land anywhere inside of it? So all of these points where the dart could hit inside the circle, all these infinitely many points is going to end up being my area that I'm really talking about, right? But it wouldn't make sense to talk about the circumference of the circle because we're saying the dart could land inside the circle and not just on the edge of the circle. So where I want, let me go different color here, my favorable area would represent the area of the circle. That's where I want the dart to go. But then I got to divide that by, still this idea of area, but what shape or shapes really could the dart land in entirely? And the dart is going to land, we said earlier, it will land inside the square. You might go, yeah, but there's a circle inside the square. True. But the circle is contained completely inside the square. So if you forget about the whole idea that there's a circle inside here, we're saying it is guaranteed to land somewhere within this square. Now, whether it lands in the circle part of the square or it doesn't land in the circle part of the square is the main thing that we're talking about here. All right, so now let me reveal a little bit of numbers in here. There we go. So the area of a circle. What was the area of a circle? That formula was what? Pi r squared. And I see right here that the radius is 6. So the area would be pi times 6 squared. And the area of the square, well, that would just be base times height. And the base times height would be the same number. But the base, we could call this piece down here. How long is that base? And if you think about the radius being 6 in this particular circle, and if I drew in another radius of 6 going this direction, then the diameter of the circle is the base of the square. So the base of the square is 12. And then if I also looked at the diameter going vertically, then that would also be the height of the square. So the base and the height are both 12. So the area would be 12 times 12 for the base and the height. So now we can finally get an answer here. So pi times 6 squared is 36 pi divided by 12 times 12, 144. Now, it really wouldn't make too much sense to say, I have a 36 pi and 144 chance of landing inside the circle. That it really doesn't give you much idea of what that looks like. So let's grab our calculator and let's figure out what is 36 times pi. And since I don't have a pi button on this calculator, I'll just do 3.14. And so that is approximately now 113.04 divided by 144. But now let's take that number, divide that 113.04 by 144. And then we get this decimal. So we don't have a 0.785 chance, but we need to multiply that by 100 or move the decimal point over 2 to the right is the same effect as multiplying by 100. And so in the end, if we want to write our answer as a percentage, we have approximately a 78.5% chance of landing in the circle. So we've got pretty good odds of landing in that circle, right? And if you look at the picture, you're like, you know what, the circle takes up most of that square, so yeah, I would kind of assume that I'd have a really good chance of that event happening. So the first answer here, what is the probability that the dart would land inside the circle? We got about a 78.5% chance. Now, the follow-up question, what is the probability of landing inside the square but outside the circle? And so that represents 4 particular regions inside the square, right? It's those yellow shaded areas. It's this part, or this part, or this part, or this part. So do we have to find the areas of those particular regions and then divide them by the 144, the total square? And no, we're gonna play this a different way. We're gonna have a big brain moment here. There's really only 2 regions that we're saying that the dart could land in. It could land inside the circle, or it's going to land outside the circle, but still inside the square. which means the total square, if we're guaranteeing it's going to land in the square, the whole square has a 100% chance. And so if I take my answer here, thank you, announcement people. If I took the whole 100%, now where'd my pen go? There it is. If I took my 100% and I got rid of the circle probability, then what's left over, 21.5%, must be inside the square, but outside the circle. So I didn't have to figure out necessarily what those kind of curved looking triangle pieces were. I figured out the piece that I could easily figure out, the circle, and then basically we used that probability and subtracted it from 100 to get what everything else must be. So there's your first real geometric probability question. Now we're going to step it up just a little notch here. So example 3, what is the probability that a dart thrown at random would hit the middle ring? And so by the middle ring, I'm talking about this orange ring. So this pink would be the outer ring, this orange would be the middle ring, and the white, I mean, we could call the bullseye, we could call the inner part. It's really up to you what you want to refer to it as. Now, the middle ring really isn't a particular shape. We haven't talked about the area of rings, but we're going to use an idea that we have talked about to figure out the area of this ring, or this kind of like donut shape. And so that ring is really a part of this bigger circle. But we don't want the area of this whole circle. There's a certain part of this circle that we don't want to consider, right? And so what if we subtracted out the area of the bullseye piece? So if we found the area of that middle circle and we subtracted away the smaller circle, what's left over would be that middle ring. So let's jump back to here. Now, the other thing that I need to probably explain here is that the radius of the small circle is 1, and the radius of the bigger circle is 2, and the radius of the entire big circle is 1 plus 1 plus 1, 3. So I just want to make that clear before we get too far into the problem. So here's how I'd first start this off. The probability of the middle ring. And I'm going to do this kind of slow but steady here, okay? So I would need to find the area of the middle ring. And we'll talk about how to do that here again. And we would divide that by the area of really the whole, the whole board. Well, what shape is the whole board? Well, it's a big circle. Okay, and it's got a radius of what? It's got a radius of 3. So we can easily find this denominator piece. It's going to be that numerator piece that's going to take a little bit of work. So we'll say that's equal to the area of the middle ring now. This is where we had to find the area of kind of that middle circle. And then we got to subtract away the area of the small circle, that white circle. So this is going to represent my numerator. And we're going to divide that by the area of the whole board, which again was the big circle. Now that big circle contains the outer ring, the middle ring, and that inner portion. It contains everything. All right, so now next step. Area of the middle circle, well that's going to be, I'll write it down here, pi times r squared. We said that had a radius of 2, 1 plus 1. And then we're going to subtract away the area of the part that's not the middle ring, which is that smaller circle. So pi times r squared. And we said the radius of that little circle was 1. And then we're going to divide the whole thing by the area of the big circle. So pi r squared, pi times 3 squared for the whole big thing. And so now I need to move some stuff here. Let me move this up a bit. So now, pi times 2 squared, well that's 4 squared, minus pi times 1 squared, well that's just 1 pi, divided by pi times 3 squared, well that's 9 pi. Well, I can subtract these two numbers up top. They're like terms, they're pi terms. So 4 pi minus 1 pi is 3 pi. and we're dividing that by 9 pi. Well, at this point, our pi's can cancel out, top and bottom, and then we're left with 3/9, which simplifies to be 1/3. So you could write your answer as this probability as a fraction of 1/3, or you could tell me what 1/3 is as a percentage. And so if you took your calculator and you did 1 divided by 3, then there's the decimal answer times 100, and it's 33.3 repeating percent. So you could say it's approximately 33.3%, or if you wanted to, you could say it's equal to exactly 33.3 repeating percent. This answer, or the 1/3 would be absolutely fine for this particular problem. All right, now the last problem. Ooh, this is going to be a fun one, and I'm leaving it for you to do, but we'll talk about it just a little bit here. So calculate the probability of selecting a point in the shaded region. Now notice there are 4 shaded regions here. And those 4 shaded regions are semicircles. Now, the assumption that we're going to make here is that if you were to select a point at random, it's going to land somewhere inside this kind of like 4-leaf clover thing. I guess I should have highlighted this in green if it was a 4-leaf clover. It's going to land somewhere in here. So I'm going to get you set up on kind of the basis here. If we wanted to find the probability of the shaded region, that's going to be equal to the area of the shaded region divided by the area of everything, the area of all the parts here. So now let's break it down. The area of the shaded part we just said was 4 semicircles. So we got to find the area of 4 semicircles. And you might go, 4 semicircles, couldn't we just call that like 2 full circles? Absolutely. If you want to do that, go ahead. Now the area of everything, well, there's really 2 different types of shapes in this problem, right? And it's not that they're inside each other. They're really like connected together like Legos here. Like we've got the 4 semicircles, that's part of everything here. Or again, you could say 2 full circles. But also, there's a square that's not shaded. So here's what you guys need to kind of figure out at this point. What's the area of the 4 semicircles? That's your favorable area. And then you need to divide it by the area of not only the 4 semicircles, but also the square included, because that's every place that we could select a random point at. Now, the next thing you might be wondering is, you forgot to give us any numbers in this problem. Oh, I didn't give you numbers, did I? So here's kind of the nice thing about probability. And you can do this one of 2 ways. You could, for instance, make up a particular number. Because that's the great thing about probabilities, is that it's a ratio. And even if I make up a number, and you make up a different number, we'll end up with the same simplified fraction probability in the end. And so, if you wanted to, you kind of need to think about, maybe the radius of the semicircle. But if the radius of the semicircle was, 2, then what would be the side length of the square? And so you can't make up too many numbers. You can't say that the radius is going to be 2 of the semicircle and each side of the square is going to be 10, because then that doesn't match up. There is a natural relationship between the side of the square and the radius of the circle. And I'll have you guys kind of ponder that idea. Another way to do this would be to not make up numbers, but to make up variables. So what if, for instance, we called the radius x? Then think about, what would the side length of the square be? It would be x plus another x. It would be 2x. And so this is where I really want to challenge you, if you want the extra challenge, is do this problem with variables. And what you'll notice that'll happen in the end is that all the variables will cancel out top and bottom, and you'll be left with a natural number. And even if you make up a number for x, for the radius, you'll still get the same answer as if you'd used variables. So we will definitely discuss making up numbers and using variables for this one the next day in class. And that is all for this geometric probability lesson.